Calculus friends. So we start off with this definition of an increasing and a decreasing function, right? A very formal calculus definition. A function is increasing on an interval if for any two values, one is less than the other. You see x1 is less than m2, x2. That implies that the y value at your first function is less than the y value at your second x. Okay, that's just what it means, that the y coming first is less than the y going second. Okay, and if it's the other way, if it's decreasing, that means that your first value is greater than your second value. Okay, so we can probably see this really easy if we looked at a graph. So here's a nice graph. Okay, there's your x-axis and your y-axis. If we have some x1 value here and some x2 value, if this y value is less than that y value, then our function is increasing on that interval. Okay, and likewise, if our first y value is greater than the second y value, then our function is decreasing on the interval. Okay, so this is a formal definition of an increasing or a decreasing function. Okay, is based upon your x's, how do the y values compare? Okay, so here's our calculus test for increasing and decreasing. If our first derivative is positive, right, it could be 9 or 47 or 0.136, but as long as your first derivative is positive, then your function is increasing. Okay, on that interval from a to b. It might be doing other things on different intervals, but on the set interval, it is increasing if your first derivative is positive. And if your derivative is negative, that means your function itself is decreasing. So we're looking at the derivative values to tell us something about our function. What is our function doing? Okay, so think about the slopes, right? The derivative is the slope of your tangent lines, and if your slopes are positive, that means that your y values are increasing one to the next. And then if we have a derivative that's 0, right, then f is neither increasing or decreasing, right? F is constant, or having a horizontal asymptote, right? So we talk about our critical values where your derivative is 0, right? It's not increasing or decreasing at that point on your interval. So exactly at that point, I guess this needs to be AB. Okay, if the derivative is 0, our function is not increasing or decreasing. Okay, so then here's your first derivative test. Okay, if we have a critical value, right, and that means that our derivative is 0, if for a critical value or a critical number, then we have these things to look at. If f prime changes from positive to negative, okay, so if f prime changes from positive to negative, so think about that. That means our function is going from an increasing function to a decreasing function. If our derivative changes from positive to negative, then what point do we have here in between them? This is called a maximum, right? Or a relative, I guess it's going to be a relative maximum. Maximum. Maybe green isn't the best to write in. So if it changes from positive to negative, we have a relative max at that x value. Okay, if our function changes from positive to, or if our derivative changes from positive to negative, then we have a maximum. But what if our derivative changes from negative to positive? Okay, that means it was going down and now it's going up. So what can we say about that point in between there, that critical value? That means that we have a relative minimum. Okay, so we're going to use the derivatives and where they change direction, right? This was similar to what we did with particle motion. Our particle can't go from right to left unless it comes to a complete stop. Okay, so this is how we know that something is also changing direction, is if it comes to a stop, if we have a critical value and your derivative changes from positive to negative or from negative to positive. So our example, find the intervals where f is increasing and decreasing. Okay, identifying all points, relative maxes and relative mins, and justify. So the derivatives are going to be our justification. Okay, where it changes from a negative derivative to a positive derivative. So let's first take the derivative of our cubic function. Okay, f prime of x equals. There is our derivative. Now we want to figure out when this is going to be 0. Okay, right? We're going to try and find our critical numbers. So find critical numbers. Those c values where we have a derivative of 0. Okay, so I have a quadratic, and the best way to solve a quadratic hopefully is to factor it. So this factors to x minus 3 and x plus 1. Right, those are numbers that multiply to give you negative 3 and add to give negative 2x. So if these are my factors, that means my solutions are at positive 3 and negative 1. Okay, so this is not a justification, so don't even try this on the AP test and leave it alone. But we have an x-intercept at negative 1 and at positive 3. Okay, but this is going to help us in figuring out whether we have a positive values or negative values. Okay, so remember, these are your critical points. This is where our graph, where our derivative, where our function has a horizontal asymptote. Okay, so it has a horizontal asymptote at negative 1 and at positive 3. So I'm going to pick a number less than negative 1 and plug it into my function, and I'm going to see if it's positive or negative. Okay, this is the mathematically way to do it, the analysis. Because doing a sign chart, which is what this is a sign chart, is not a mathematical justification analysis. So what happens when I plug in negative 2 into my derivative? That means my derivative is positive on the left side of negative 1. Okay? And then I'm going to do the same thing for two other numbers. I'm going to use 0, right, because that's in my interval from 1 to 3. And I'm going to find the derivative value at 0, which is just going to be negative 3. And then I'm going to do the same thing for maybe 4 or 5 or 6 or anything to the right of 3. No, not 6 or 7. 4 to get 4. No, that's 16.
Wait, if you plug in 0.
So here we go. At negative 2, I have a positive 5, which means our derivative is positive on the left of negative 1 on this interval. Okay, in between negative 1 and positive 3, our derivative is negative, right? Negative 3. And to the right of positive 3, our derivative is positive again. So let's take our values and come over here and find out the intervals where we are increasing. So f is increasing. We use the exact words that they write. F is increasing on what intervals? Okay, so we have the first one from negative infinity until we get to negative 1. Okay, increasing on that interval, and where else?
3 and infinity.
Positive 3 to infinity. Okay, so those are both your answers, from negative infinity to negative 1 and from 3 to infinity, because our derivative is positive. Okay? We have a positive 5 if it's less than negative 1, and we have a positive 5 if it's greater than 3. Okay, so those represent all of our values. So we have these two intervals, and this is your justification. Okay, with all of your math down there below. Our derivatives are positive, so f is increasing. And we're going to say a similar thing for our decreasing intervals, but because our derivative is negative. So there's your interval of decreasing. And the last thing we have to do is talk about your maxes and your mins. Okay, so here we have an increasing to a decreasing. That means we have what type of a point at negative 1? From increasing to decreasing is a max. So we write f has a relative max at what x value? At x equals negative 1, because f prime changes from positive to negative. Okay, or you can write you can literally write the word positive or POS, and you can write negative or any G. Those are your acceptable reasons. F has a relative max at x equals negative 1, right? We don't care about what the y value is. We care about what x value is the maximum at. So at x equals negative 1, because the derivative changes from positive to negative. And using that similar type of reasoning, where would f have a relative minimum? At positive 3. X equals positive 3 because f prime changes from negative to positive. So there we go. Okay, now it says use the results to sketch the graph. Okay, so let's do a little graph here. Let's put our axes on there. Here's your y-axis and here's your x-axis. Okay, negative 1. Okay, this is a point there at negative 1, and here's our point at 3. So these are your maxes and mins. These are your critical points. Okay, I know that my graph has a maximum somewhere along negative 1, and I can figure out exactly what it is by plugging negative 1 into my function. Right? We just have to plug negative 1 into that for all the x's, and it will tell us exactly where that y value is. Okay, but I'm not going to do that. I just know that it has a maximum at negative 1 and a minimum at positive 3. Okay, so my function might look something like that, right? Depending on what that actual y value is from when you plug it in and what the actual y value is at there, which I did not do. But your calculator can help you do that to figure out exactly where your maxes and your mins are. Okay, so here we have a different function. It's x squared minus 4 to the 2/3 power. So this is the cube root of our silly thing squared, right, if we want to get technical about it. So let's do our math. Our first thing is to take the derivative. So this is going to be a power rule plus a chain rule. So 2/3 of x squared minus 4 raised to the negative 1/3 power, because 2/3 minus 1, 2/3 minus 3/3 is negative 1/3, times the derivative of x squared minus 4, which is 2x. Okay, so we could leave it like that, but let's do a little more. So this is 4x in your numerator. I got that by doing my 2 times my 2x, right? That's 4x. All divided by 3 times the 3rd root of x squared minus 4. Okay, So our negative 1/3 power brings our whole entire parenthetical thing to our denominator, and the 1/3 power is also known as the third root. Okay, so if this were a free response question, you would get 1 point for doing the calculus correct, okay, which basically stops here, but we're going to simplify it. And we want to know what are the critical values, so where does this equal 0? Okay, where does that equal 0? So let's do our multiplication. We're going to multiply by our denominator. Right, so 3 times that thing is, basically we want to know when our numerator is 0, and that happens when x equals 0. Okay, so we basically, maybe we just have one critical value, and it's going to be 0. Okay, because 0 divided by anything is 0. So if our top is 0, that means you have a 0 as your answer, no matter what is in the denominator. So let's check. Let's plug in -1 and see if we get a positive or negative. Let's plug in +1 and see if we get a positive or a negative. So my calculations say that my function is increasing on the interval from -infinity to 0 because our first derivative is positive. And my function is decreasing from 0 to infinity because my derivative to the right of 0 is negative. Which means that what type of a point do we have at 0? If our function goes from increasing to decreasing, that means we have a relative max at x equals 0 because f prime changes from positive to negative. Okay, so f has a relative max at x equals 0. And if you wanted to figure out what that y value is, you could plug 0 in to find that extrema. Right? So that would be our relative maximum. But because it has one point where it's increasing and then decreasing, this has to be your absolute maximum also. Because it's always increasing to the left and then it's always decreasing to the right. So it has one high point right there at 0. Okay, so our first derivative tells us where our function is increasing and decreasing, and where we have maxes and minimums, where your first derivative changes signs. Hey, sorry y'all, I forgot about some things, and that's that the critical values are also where your derivative is undefined. So we have to take our denominator, right? We have to take our denominator and see when it's going to equal 0 also. Okay, so we have a +2 and -2, so we have to add some intervals to our problem. Okay, so we have to check and see what's going on to the left side of -2, right? Maybe -3, and we have to check and see what's going on the right side of +2 to see whether our graph is really still increasing or decreasing on those intervals. So let me come up here, I'll do that up here. I'm going to check f prime at f prime at -3, and I'm going to check f prime at +3. And I think our intervals are going to change a little bit, right? If we do this, we get a -12 on top, and then -3 squared is 9, so that's going to be a positive on the bottom, which means that we are negative to the left side of -2. And if we plug in a +3, that's a +12 over a positive is going to be a positive. So yes, we are changing our intervals here based upon my brain. The reason is still the same. It's increasing because the derivative is positive, but our intervals of positivity are changing. So we had positive to the right. So we are increasing from -2 to 0, and then again from 2 to infinity. Sorry, that's an infinity. Okay, that's where our graph is positive. So it was positive between -2 and 0, and positive between 2 and forever. Okay, so it's going to change our, sorry, there's the bell calling kids to go to class. It's going to be decreasing on, well, from -infinity to -2, right? Because it's negative over here. And then again, it's decreasing from 0 to +2. So these are our two intervals where our function is decreasing, and our other two intervals where our function is increasing. Oh, my poor brain. Okay, so not only is it where it's 0, but our critical values are also where your derivative is undefined. Okay, those are our critical values that we have to check and see whether our graph is increasing or decreasing on those intervals based upon our derivatives. All right, there we go. Goodbye.